Hey, Mr. Robinson.
Good morning. All right, welcome in, everybody. I'll take attendance in a few minutes, but I'll go ahead and start now by talking about the warm-up. So item number one, I've defined two matrices, and normally you'll get a defined matrix that's a capital letter, just out of tradition. It doesn't really, mean anything or matter. And so in a world where matrix A is defined as being 4, 3, 2, 1, and matrix B is defined as being 6, 3, -2, 4. Solve for matrix C for me, where C is defined as being equal to 2A minus 3B. Good morning. And then on top of that, not only do I want you to find all of matrix, but also tell me what is entry 2, 1 of matrix C. Just a quick vocab check in terms of how these terms down here can name out specific positions within a matrix. And then item number two, this is like a open-ended concept question. This isn't something I talked about yesterday, but I think this is something that you can figure out for yourself pretty easily. So if vector C, and this is not the same C, different question. I guess if I was more responsible, I would have used a different letter. But nonetheless, if vector C is equal to 6, 7, right, such that it's this vector right here in the xy plane, x, y, what do you think vector D is if I'm defining vector D as being 1, 2, -3? Think about it, write down a little written response for question number 2 there, just a few sentences on your thoughts. Then we'll go over item 1, we'll talk about item 2. We'll wrap up the notes real quick by talking about matrix multiplication. And with whatever time is left of the hour, we'll just hang out and do homework questions. And if you holler out any homework questions, I'll gladly solve them for y'all here in stream. Any questions on that stuff or what we're doing today?
No, sounds good.
Cool.
Good morning, Mr. Rob.
Good morning. Okay. No, okay, that's the one that I want for this class. Okay. Before we start, does anybody have any just like general questions, state of the world stuff about this class, stuff about where you're going to school next year? Since this is still technically y'all's homeroom, this is like the place where you can ask those kinds of questions and get honest answers.
Oh, Mr. Robinson, actually, quick question. About the SAT stuff.
Yeah.
Are all colleges required to like not accept it? Like, are all of them willing to not accept SAT scores?
So required is probably the wrong word to use when asking that question, only because it's really important to keep in mind that the College Board, even though they seem super official, they're not a governmental organization. They're a private company that just happens to occupy this space where everybody relies on them for this stuff. So they have no like force of law behind that test
Right.
or anything they do at all. So from the beginning, colleges accepting their scores as being valid or whatever was always optional. It's always been like a business or a competition or whatever between them and the people who offer the ACT. But I have not heard of any cases where
Like, for example,
I'm pretty
USC
sure
or UCLA.
I'm pretty sure every single college is waiving it. My wife knows more than I do, definitely on this topic. I'll ask her today when we have lunch, and I'll update you tomorrow. But to the best of my knowledge, every major university that you've ever heard of is saying that, hey, you're cool if you don't have an SAT.
Okay, cool.
And I'm sure it's like right at the intersection of everybody was starting to realize over the last decade that SAT scores are kind of worthless anyway in terms of like determining how well you're going to do in college, so who cares? Mixed with the fact that even though you could theoretically have already taken the SAT and already have a score in your pocket, which I know some of you already do, right? So some of y'all have scores that you can submit. More than like 75% of people who apply to college don't end up taking an SAT until like their senior year summer, where they like start caring about it in those last few months. So I'd be willing to bet the overwhelming majority of people would be going into application time not having taken an SAT, which would really hurt their application numbers, you know? Just because like, I don't know, all that stuff is due by November. And I think reasonably that leaves like 2 months after the world begins getting back to normal where you could take your SAT. Like I don't see stuff going back to normal or opening up completely until about September, August or September. So yeah, reasonably you would only have September, October, November to take your SAT before UC applications are due. I just don't think it's gonna happen. I'm pretty sure they're all gonna waive it.
Nice.
Yeah, kind of, yeah, but it just means that you're relying on your GPA, or if you already have your SAT score, it shows that you don't procrastinate, that you like just get stuff done. So if you have a score that you can submit, great. And if you don't, I don't think it'll count against you.
All right.
And for all of y'all who are deciding to go to community college straight away anyway, I guess that never mattered, right?
Yeah, exactly.
It's a nonsense test anyway. Anyway, let's go ahead and get started. So item number 1 here is a pretty straightforward computation. All we're being asked to do is calculate what 2a minus 3b is. Now, you got to keep in mind when it comes to adding and subtracting matrices that those matrices have to have the exact same dimensionality. And luckily, that's the case here. Otherwise, there would be no problem to do. This is what we call a 2 by 2 matrix. This is also a 2 by 2 matrix. This is scalar multiplication, and this is also scalar multiplication. And scalar multiplication isn't going to change the dimensionality, right? The size of the matrix. And so no matter what, in the end, by the time we get to this step, all that we'll actually be doing is the subtraction of two 2 by 2 matrices. So I'll do the scalar multiplication part first. So that is to say, if C is going to be equal to 2A minus 3B, well, I'm going to need 2A. So I'm going to take everything inside of A and I'm going to double it. So this is going to be 8, 6, 4, 2. And then from that, I want to subtract 3B. And again, this is just a step of scalar multiplication. So I'm going to multiply this 3 into B here. So this is going to give us 18, 9, -6, and 12. And then to subtract two matrices is simply to go through position by position to every position that corresponds and subtract the values. So this is going to be equal to 8 minus 18, which is -10, 6 minus 9, which is -3, 4 minus -6, which is +10, and 2 minus 12, which is -10. And so this right here is matrix C. Are there any questions on this first part of the warm-up? No? Okay. And just a vocab check, what is C21?
10.
Yeah, and how do you know?
Because it's the second row,
Yep.
Second row, first column.
first one.
Perfect, yeah. Whenever we're looking at this matrix stuff, it's always row by column, and that's a lesson that we'll get to employ in a different context today. But yeah, this means what is in matrix C inside of row 2, column 1. Right here, this +10 is C21. It's really important to be able to read matrix entries like that. As you'll find when you get to more complicated mathematics, there's a whole bunch of formulas that refer to specific entries within a matrix by some sort of system. So it's good to know how to read that stuff. And then item number 2, just an open-ended concept question, like I said, like the goal of having students who can do math is the fact that they can use those skills to figure out stuff for themselves. So if C is a vector with the entries 6, 7, right? This would be enough information to get its magnitude. We could use the Pythagorean theorem to do that. We could also get its orientation by using inverse tangent. If you really needed, you could figure out this theta. Can I have somebody take a guess? What do you think D 1 to -3 is?
Isn't it going to be something three-dimensional?
There we
You
go.
have X, Y, Z.
Yeah. So D is talking about some kind of 3D vector. Which is to say it's a length of 1 in the X direction, a length of 2 in the Y direction, and a length of 3 in the Z direction. And in order to make this point more visual, let me show y'all some computer stuff. Not that, this, okay. Anyway, so this right here is a vector sketcher, right? Like a piece of graphing software, but designed specifically for vectors. And right now we're viewing it top down. So this blue vector right here, this is the blue vector 6, 7, the one that I defined in the warm-up. And you'll notice that it lays flat on the XY plane, right? Just regular old graphing. However, because this is in 3D, I can rotate it. And you can see that the way that I input it here is 6, 7, and then 0, which means it's a length of 0 in the Z direction. So it doesn't come out of the plane of the page at all. It is perfectly flat in the XY plane. However, vectors are capable of being three-dimensional, right? Like if I do this with my arm in this room, I'm pointing in a three-dimensional vector direction, considering we live in a three-dimensional space. So if I pop in here 1, 2, -3, and hit draw, it'll draw the red vector, and that's our second vector that I named in the warm-up, vector D. And you can see here that this vector, this red one, it sticks out of the plane. It has a little bit of length in the X, a little bit of length in the Y, but it also goes below the Z-axis in that negative direction. So these vectors, they can be used to represent things that point in a direction in 2D space and in 3D space. And the wackiest thing about vectors is that they could have infinite dimensional space. Now, you can't draw that. You can only actually draw a one-dimensional, a two-dimensional, or a three-dimensional vector. However, the math for four-dimensional vectors and higher follows all of the math of the lower dimensional vectors. You just can't draw or imagine them because your brain is sadly a three-dimensional object trapped using three-dimensional logic.
Hey, how about that?
Anyway, cool. Are there any questions on either part of today's warm-up? No, Mr. Rob, it's a great warm-up. Okay, kids. So let's go ahead and move on today to the last item of the notes, and then we'll have the rest of whatever time we have to work on the homework. This assignment's pretty straightforward, so I won't like give tomorrow for it or whatever. Though if you're not done with the homework, you could ask questions at the top of the class tomorrow, and I'll work them out. And I'll extend the homework so that it's due tomorrow night, but just know that tomorrow we're going on with section 6 notes. Nonetheless, today we're going to talk about 9.5, and this is just going to be continued from yesterday's notes. And in yesterday's notes, we talked about matrix addition, subtraction, and scalar multiplication, which that first part of the warm-up that we did today had all three of those things in it. The only thing to consider past what we did is the fact that if you have matrices of different sizes, you can't add them or subtract them, just because when we add them or subtract them, we're lining up the entries one by one, and if they're different sizes, then there will be entries that don't line up in one matrix to another. Today, however, we're going to talk about matrix multiplication, which is a fundamentally different operation than scalar multiplication, which we talked about yesterday. Matrix multiplication has a whole bunch of its own rules. So the first thing to consider is that if we are multiplying two matrices, so when multiplying two matrices, the first thing that we have to consider is the dimensionality of those matrices. When multiplying two matrices, we must consider their sizes, which I guess to talk about the size of a matrix is the same thing as the dimensionality. It's just that the dimensionality is the fancy, technically correct math word. Now, when multiplying two matrices, let's say that they have a particular size to them, here is the rule that has to be observed. If I want to take matrix A and multiply it by matrix B, where matrix A has the following dimensionality. Let's say that matrix A is a size P by N, which is to say it has P rows and N columns. And matrix B is size N by M. In this case, I know that matrix multiplication is going to be possible. Here's why. We need these dimensions right here to be exactly the same. These must be exactly the same. As long as the columns of A is equal in size to the rows of B, then matrix multiplication is going to be possible. And the product would be some new matrix C. These outside terms right here, that's going to tell you how big the final matrix C is going to be. So we know that matrix C here will be P by M in size. So that is to say, just because I know that, like, you know, sometimes it's not the easiest thing to see what this is talking about with just variables. If matrix A had some size 2 by 3, and matrix B had some size 3 by 5, right? Then if I were to do A times B, this would give us back some new matrix C, which was 2 by 5 in size. And notice the following. What would happen if I multiplied matrix B times matrix A?
It'd be five
It would become
5 by
2
2.
times 5.
So a natural response is that it would be 5 by 2, that it would
It
just
wouldn't
be,
work.
well, the same thing but flipped. But it's actually that second one. Wait, who said that?
It wouldn't work.
Why wouldn't it work, Alex?
It's 3 by 5 and 2 by 3. It's not the same.
Exactly. So if we go ahead and identify the fact that B is 3 by 5 in size and A is 2 by 3 in size, yo, these inside indices, which is just like the pluralization of the word index, these don't agree, not the same. And if those two inside values are not the same, then there is no multiplication. You can't do it. This is to say that yesterday we talked about all of the properties that scalar multiplication have. The idea that scalar multiplication is associative and distributive and commutative, that when you do scalar multiplication, it's going to obey all the normal rules of multiplication that we are accustomed to. But this right here is telling us that A times B is not necessarily equal to B times A, which is to say that matrix multiplication, if A times B is not equal to B times A, this is the same as saying that matrix multiplication is not commutative. Matrix multiplication is not commutative. Okay, so now we know what the rules are about what allows two matrices to be multiplied or not, right? However, it's a very different question to then talk about, well, what does multiplying matrices actually look like, right? And here's how we do it. The same way how when it comes to writing down the size of a matrix, right? We are interested in the number of rows by the number of columns. When it comes to matrix multiplication, matrix multiplication is done the same way. It is also done row by column. And without getting into a fancy definition thing where all of the terms are just left alone as variables, let's just start off with a numeric example. So let's go ahead and say that, for example, we are asked to multiply matrix A times matrix B such that matrix A is 1, 2, 3, 4, and matrix B is 5, 6, 7, and 8. Now, the first thing that we want to go ahead and realize is, one, is matrix multiplication possible here?
Yes.
Matrix multiplication is possible here, and we know that to be true because this is a 2 by 2. This guy is also a 2 by 2. These inside numbers, they match. And so the outside numbers are going to tell us what the outcome is going to be. So we know that the matrix that we are building here should also be some kind of 2 by 2. That part's nice and easy. And now for the actual act of going through and multiplying these two together. Now, the way that I think about this is that the first matrix is going to contribute its rows. So matrix 1 is going to provide row 1. Matrix 2 is going to provide, matrix 1 is also going to provide a row 2. Over here on the right-hand side, this matrix is going to provide columns. So it's going to provide a column 1, and it is going to provide a column 2. And so when we multiply these matrices together, if you want entry 1, 1 of the new matrix, entry 1, 1 is going to be made of the product sum. It's both of them. You have to multiply terms and also add terms. But if I want to know what is going to go up here in 1, 1, we are going to build it by using row 1 and column 1. So that is to say that 1, 1 of our new matrix is going to be equal to 1 times 5 plus 2 times 7. And we're going to go through and we're going to follow that same pattern until we can build out all 4 values. And so if I want entry 1, 2, we're going to use row 1 with column 2. So this is going to be 1 times 6, 1 and 6, plus 2 times 8. If I want entry 2, 1, we're going to use row 2 and column 1. So this is going to be 3 times 5 plus 4 times 7. And then finally down here, bottom right, if I want entry 2, 2, I'm going to use row 2 and I'm going to use column 2. So this is going to be equal to 3 times 6 plus 4 times 8. And so the final step is to go through and simplify all of that work to get our final product matrix. And this is to say that our final matrix here is going to be equal to 19, 22, 43, 50. Are there any questions on this example or like what this technique is asking us to do?
No, it's pretty good.
Okay. And just a quick show of like a GIF of what you want to be going on in your brain, how it is I build out those 4 values. I think this is really illustrative. That the thing that builds out these individual values is the fact that we're taking the row from the first matrix and we're hitting it against the columns of the second matrix. Rows of the first matrix, hitting them against the columns of that second matrix. Let's go ahead and do a second example together. A slightly longer one, and then I'll be done talking about matrix multiplication. Okay. Let's go ahead and say that I have 2 matrices, matrix C and matrix D. Actually, no, I'm using the top letters of the alphabet too much. Matrix M and matrix N. I have a matrix M, which is equal to 1, 0, 2, 3. And I have a matrix N, which is equal to 4, 3, 2, 6, 0, -1. And what I would like you to do is give me MN and give me NM. Let's take 1 minute on that. Two minutes on that. Yeah, take a 120-second head start, and then we'll dig into it. Okay, Y'all ready to begin? Let's go ahead and start with matrix NM first. What is matrix N times matrix M?
No solution. You can't.
Yeah, and I mean, it's mostly because y'all are either going on to senior year or college, but I'm going to be picky about your language. It's not technically no solution. The time when you use the phrase no solution is if you are attempting to solve for a variable, right? And if you cannot solve for the variable, if it has no solution, that's the phrase that we use there. Technically, since there's no variables here, right? All of these numbers are defined. It's just no product.
All right.
Or no operation or something like that. But here's why. What's the dimensionality of matrix M?
2 by 2.
2 by 2.
That's a 2 by 2. What's the dimensionality of matrix N?
2 by 3.
That homie is a 2 by 3. And these two numbers here on the inside do not match. So there is no product. However, we can totally do M times N, because this first one is a 2 by 2. The second one is a 2 by 3. These inside numbers here, they agree. And so when I multiply these two matrices together, what's the dimensionality going to be of the total product?
2 by 3.
This should produce for us in the end a matrix which is 2 by 3 in size. So, and I recommend you do the same. I mean, you know, you're your wife, you're gonna do what you're gonna do. But I had a really hard time seeing this because, yo, man, and you know, God bless his soul if he's still out there teaching, but my pre-cal teacher in high school, this is one of those things that he skipped. And then I got to UCLA, and then, like, for real, day one of one of the physics classes I was taking, professor's like, hey, you guys are all good with matrices, right? And the whole class, a class of like 350, everybody's like, yes. And then I'm just like really sadly in the back row because I was always like a back row person in undergrad. I'm just like, no. So I had to like teach myself all of this stuff in a week. And at the beginning, I just could not see it. Highly recommend highlighters. It is the rows of the first matrix multiplied by the columns of the second matrix. I just think it helps keep in line which pieces we're putting together. So nonetheless, let's go ahead and build out all 6 entries of this matrix. So it's going to be row 1 times column 1 in order to get that first position. So here's our matrix with its 6 entries. And so it's going to be row 1 times column 1. So that's going to be 1 times 4, which is 4, plus 0 times 6, which is 0. And then our next entry is going to be row 1 times column 2. So that's going to be 1 times 3 plus 0 times 0. So that'll be 3 plus 0. And then it's going to be row 1 times column 3. So that's just going to give us 2 plus 0. And now for the second row, it's going to be this row times this column. So it's going to be 2 times 4, which is 8, plus 3 times 6, which is 18. And then it's going to be row 2 times column 2. So that's going to be 2 times 3, which is 6, plus 3 times 0, which is 0. I think you're very quickly finding that zeros are our friend when it comes to doing these types of matrix operations. You will see a lot of zeros when it comes to larger matrices, and you will see a lot of zeros on tests and quizzes just because it makes it more reasonable to do these operations quickly by hand. And then finally, row 2 times column 3, 4, plus 3 times negative 1, so that'll be minus 3. And we get here that our final matrix is going to be equal to 4, 3, 2, 26, 6, and 1. Is this okay?
Yep, pretty straightforward.
Yeah, and as I will continue to scream, if you have any hopes or dreams of engineering or for some reason physics, which like don't major in physics. As somebody who majored in physics, maybe don't. I mean, unless you want to, in which case have fun. But matrices, matrix operation, and the logic of how they work is the fundamental underpinning to that stuff. So be sure to get good at this, especially if you want to go into an engineering department somewhere. Last thing I'm going to talk about today. Could y'all take out your graphing calculators, please? I don't want to do the horrible thing that all of my teachers used to do. I've complained about this to y'all before, of like, hey, you know that really hard section of stuff we just went through? Well, guess what? Your calculators can do it trivially, haha. Let me just show you. Your calculators can do every single one of these matrix operations trivially, and you should know that so that, you know, you always know what the final answer is. It won't give you the steps, but it'll give you the work, and that's, I'm sorry, it won't give you the steps, but it'll give you the answer, and it's nice to have that peace of mind, especially when you find that some of these matrix operations might take 5 or 6 minutes just to do one problem. And it's really easy to make one little fiddly mistake with either, oh, I multiplied wrong here, or I added wrong here. It's nice to have a device show you what the answer is so you know what you're working towards. Nonetheless, everybody have their calculators out? Can y'all see the calculator screen that I'm sharing?
Yeah. Mm-hmm.
Yeah, and then when I put the mouse over it, can you see the mouse pointer?
Yeah. Mm-hmm.
Okay, yeah, okay, good, good, good. Okay, so on our calculator, we're gonna quit out, and just so that we can go to the home screen here. And what I'm going to do is I'm going to hit second matrix, which is this command down here. And you'll notice that it's going to give us a list of matrices, yeah? And so what I'm going to do is I'm going to hit enter on matrix A. And then I'm going to hit enter again, and it's going to display what that matrix is. And you'll notice that it gives us back an undefined, unless your calculator already has its matrices defined in it. So what we're going to have to do is we're going to have to go back, hit second matrix, and be like, okay, well, what is, sorry. Clear, quit, second matrix. Okay, so now we're going to have to edit our matrices. So I'm going to go over here to edit, and I'm going to choose edit option 1, edit matrix A. And the first thing that it's going to ask us, well, how big is matrix A? So what I'm going to do is I'm just going to do this last warm-up question that we did. So I'm going to turn matrix A into that matrix M, and matrix M was 2 by 2. And after I tell it the size, it'll give us the correct number of positions for us to enter the entire matrix. So that's 1, 0, 2, 3. And once I've done that, it has saved our matrix. So I'm going to hit second matrix just to go back to the previous menu. And you'll notice that it has a stored matrix in it, and it'll show us how big that matrix is on the side. Now I'm going to go over to edit, and I'm going to edit matrix B, which again, I'm going to use the same matrix as that previous example. And that matrix was a 2 by 3. So now you'll notice that when I put in a different size dimensionality, it'll give us the correct number of boxes again. And this matrix is 4, 3, 2, 6, 0, -1. And again, I'm now just going to hit second quit just to go to the top menu, because it kind of saves as it goes automatically when it comes to the matrix options. So the first thing I'm going to do is let's go ahead and do matrix B times matrix A. So I hit second matrix, choose matrix B, hit enter. Hit second matrix, choose matrix A, hit enter. In the same way that putting two numbers side by side on this screen, like 4 parentheses 7 would just give us back 28, putting them side by side is enough for the calculator to know that you're talking about multiplication. You can also use the multiplication sign in between them if you want, but it's unnecessary. And in the last example that we did, what was the product of the second matrix times the first matrix?
No product.
No product. And you'll notice that if you try and have your calculator do a thing that would give you back no product, it's just going to tell you dimension mismatch. That is to say that it checked to see if those two inside numbers on the sides were the same. They weren't, and so no product can be taken. I'm going to hit second quit to, I'm just going to hit 1 to quit to go back a menu. Now I'm going to do second matrix A times second matrix B, and it can do our matrix product for us. You can also use your graphing calculator to do things like scalar multiplication. So if I wanted to, if you were doing one of the easier homework questions and it was like, hey, what's 4a? It can also do that. So literally every single one of the operations that we're learning this section to do by hand can also be done by using your graphing calculator. Are there any questions on matrices, matrix multiplication, addition, subtraction, vectors, or using your graphing calculator to do these basic operations?
Mr. Robinson, how do you clear matrices?
Oh,
on
it's
the
a great
calculator?
question. It's a great question because it's hella complicated. Yeah, so it's really wild how they did it. The way that you delete matrices is not in the matrix menu at all. So if you
Okay.
went to the matrix menu and you like went over a matrix and hit delete, you would expect that to do a thing because y'all grew up in a world with touch screens. Nah, this was made to be unnecessarily difficult. Here's the deal. I'm gonna hit second, and then it's all the way down here in the bottom right where that plus sign is, memory, M-E-M, mem. I'm gonna hit second, memory, and if you hit clear all entries and hit enter, this will clear all of your lists and all of your matrices. Oh, wait, what? I'm sorry, clear all entries does not clear the matrices. Clear all entries only clears, clears out your lists. Huh. Let me double check. I forget how to clear matrices. Oh, no. It is that menu. It is that menu. So it's second, memory. And then option 2 is memory management / delete. But if you were to scroll over,
click 5.
yes. And then under this option, we can clear out matrix with option 5. And yeah, you can clear out these 2 matrices.
What do those numbers represent? 47, 65.
They tell you how many bits of data they take up.
Oh,
So bigger,
right.
it's so little, it like doesn't matter. But yeah, it's just telling you how many, how much space each one of those matrices takes up. Are you sure? Yes. Yeah, second, memory. The other thing you can do, and the thing that I usually do with my graphing calculator, is I just overwrite them. So I usually use A and B for the ones that I'm doing operations with, and I just like leave it stored in there until I need it again, because you can always just go back to it and overwrite it with what you want your new matrix to be. But yeah, memory management, option 5, clear a matrix, delete that matrix, yes. Yeah.
Wait, Mr. Robinson, where does it say clear matrix? Because
you hit
on the
so yeah.
On that last screen, it just like gives you an option to select the matrix.
You hit delete, the delete key.
Oh, okay.
And then it'll give you a pop-up with a yes and a no.
Okay, yeah, got it. Thank you.
Great question, yeah. So yeah, this means, just like the last quiz, since we have an easy way to know what the answer is every time, when it comes to people grading the work that you do for matrices, they allow you to have a calculator. That means we're not checking your answer, we're checking your work. It's important not only to be able to get the correct answer, but to know how the correct answer itself is gotten, which is why when I do the chapter test at the end of this, I will be looking for this kind of formal laid out work so I can see the steps that you took to get here. If you go straight from here to there, while it is totally possible to do that in your head with a little bit of practice, I will be expecting to see these intermediary steps both in the homework and on the test. We have like 10 more minutes to hang out, so we'll just hang out for the next 10 minutes. If you have questions on the homework, holler. I'd be glad to answer any of the questions on stream. But other than that, that's it in terms of notes. Feel free to hang out and work on the homework. If you have questions, just holler. Otherwise, have a nice day, and I'll see y'all tomorrow for the next section of notes. Let me go ahead and extend out the homework one day like I said I would before I forget. Oh, it's already due tomorrow at 10. Okay, that's fine. Whoa, whoa, that's scared. Oh man, we have our printer set up on the wireless network. And I guess my wife is downstairs. She just hit print on something that she needs a paper copy of, and the sound of the printer turning on behind me scared the crap out of me for a second. Also, to Classroom, I'm going to post a link to that little video that I played, the one of the numbers moving for the matrix multiplication, just because I think it's a good thing to have burned into your brain. That's always how I think about matrix multiplication whenever I have to do it, which I find myself having to do it a lot because of what physics, the type of math that physics asks you to do. It's one of the GIFs I keep in my secret teacher GIF folder.
Mr. Thompson, if you're adding or subtracting, the dimensions need to be exactly the same for the row and column, right?
Correct. Yep.
Okay. Okay, just wanted to make sure.
Yeah, because if either one is different, then you'll have hanging entries on a matrix that don't align. And so you'll be adding 3 with nothing, you know?
Okay. Yeah, yeah.
Huh. One, two, three, four, five, six. Huh. There's only 6 weeks of school left. That's wild. Yeah, and I have finals in 3.5 weeks. So I have my finals before you guys, which I guess that's good. I'll have to study probably starting this week for that stuff. But I'll be done with my stuff by the time I need to write and grade your guys' stuff. Hey, anyway, just some thoughts. Y'all have a nice day. I'll see you tomorrow at the same time, same channel. Tomorrow when we come in, we'll be talking about a technique called Gaussian Elimination, which will allow us to use matrices in order to solve for systems of linear equations in a way that's more efficient than just regular old elimination. And I think one of the coolest things about matrices is that they have a way that we can check to see whether or not a problem is solvable before we even begin solving it. Y'all have a nice day. Homework's not due until tomorrow, so tomorrow at the start of class, I'll take questions on it. But yeah, y'all have a nice day. I'll see you tomorrow.
Thank you.
Bye, Ms. Robinson.
Mhm.
See you.
You.